Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with number 29 here in your homework. So basically when you read it, we've got this car traveling at 60 miles per hour and the driver hits the brakes. Now you can see from these snapshots here, right, the delta x's, this distance. See how the delta x's are getting smaller, meaning the velocity is decreasing. Whoops. Sorry about that. I'll get back to that problem. There we go. So start by sketching a velocity graph. Velocity against time. Now, you're going to want to start this by converting these to feet per second. Those would be just good appropriate units to work in. You can work in meter per second if you wish, but I wouldn't leave it in miles and hours. Once you have those, right, at t equals 0, you're going to have a number here in feet per second. You're going to have another one here 5 seconds later. And go ahead and use our standard, constant acceleration assumption. So your graph should look something like this. Okay, now the total distance covered in the 5 seconds. So the total delta x can be found from this area, which is a piece of cake. Okay, it's a trapezoid. Hopefully you've watched my videos on how to find the area of a trapezoid. All the numbers there should be there. So you can get a number for that pretty easy. Now the 2 seconds is going to be a bit more work here. So, and also, by the way, you'll notice something about v of t and x of t. So what that means is you're to try to find a function that tells the velocity anywhere in this picture, not just the endpoints. Same thing with the x of t. So what we're going to do in our graph, we're going to back up a little bit and just pick kind of a generic point on the graph. And that red distance, I'll just draw it like this, that red distance on this graph is the v of t. Now, a couple ways to find that. Here's one. Notice that this is a linear function, and I'm talking about this. All right, so linear functions, if we think back to algebra class, y equals mx plus b, except instead of y, the vertical axis is v. The m is the slope. I'll just leave that for a moment. The x is the t, and the b is the intercept. The intercept you can get right there. Just read it right off the graph. The m, remember, is slope. So you can get the slope just by using these endpoints here. And you're going to get a negative number, which is just fine. So if you do those things, you're now going to have v equals a number times t plus a number. This one should be a negative number. Right, just look at the graph, see that has negative slope. So there's your v of t, that's how you get that, boom. Now the x of t, that one's a little trickier even. Right? So remember the delta x, let me do this one in green, different color here. I like color coding work. So the delta x is going to come from this area here. And it will be a function because the location of that right-hand side is a function. And remember, for a trapezoid, you take left plus right, divide by 2 times the width. Hopefully you've seen my video on how you get the area of a trapezoid. Now the left is a number. It's this number you're going to read right off the graph. The right, this is this distance right here. Now we don't have a number, we have a function, but that's what you found here. So just put that in, divide by 2 times the width. The width now, instead of 5, we're just going to call that t. When you put those all together, you should get an equation. It's going to look like a number times t minus another number times t squared. I'll just write it like that. And you folks can kind of compare when you get it right. And then once you have those, you can just put in 2 seconds. Here to get the velocity, here and here to get the delta x for the car. So that should get you through this. That's a tougher problem, quite a bit more work, but I hope that helps. Have a great day.